Hello everyone, myself Pavitra Vyas from Department of Information Science and Engineering, Sri Venkateshwara College of Engineering. Today I am going to explain about mutation analysis and fault-based adequacy criteria. Mutation analysis. What is mutation analysis? Mutation analysis is a form of white box testing in which the testers change some of the specific components of an application's sources code to ensure a software test suite can detect the changes. Mutation analysis is the most common form of software fault-based testing. A fault model is used to produce hypothetical faulty programs by creating variants of the program under the test. Variants are created by seeding faults, that is, by making a small change to a program under test following a pattern in the fault model. The patterns for changing the program text are called mutation operators. Each variant program is called a mutant. The original program and the mutant program, both are compared and the result is the output of both the programs. Mutation analysis. Here are few terminologies which are included in mutation analysis. Firstly, the original program under test, which means the program or the procedure to be tested. Mutant, a program that differs from the original program for one syntactic element. For example, it may be a statement, it may be a condition, a variable, or a label. Distinguished mutant, a mutant that can be distinguished for the original program by executing at least one test case. Equivalent mutant, a mutant that cannot be distinguished from the original program is known as the equivalent mutant. Mutation operator, a rule for producing a mutant program by syntactically modifying the original program. Mutants should be plausible as faulty programs. Faulty, which means a fault model is an engineering model of something that could go wrong in the construction or the operation of a piece of equipment. Mutant programs that are rejected by a compiler or that fail almost all the tests are not good models of the faults we seek to uncover with systematic testing. We say a mutant is valid only if it is syntactically correct. A mutant obtained from the program of figure 1.1, which is in the next slide, by substituting while for switch in the statement at line 13 would not be valid since it would result in a compile time error. We say a mutant is useful if, in addition to being valid, its behavior differs from the behavior of the original program for no more than a small subset of program test cases. A mutant obtained by substituting 0 for 1000 in the statement at line 4 would be valid but not useful since the mutant would be distinguished from the program under test by all inputs and thus would not give any useful information on the effectiveness of a test suite. Defining mutation operators that produce valid and useful mutation is a non-trivial task. Non-trivial meaning having some variables or terms that are not equal to 0 or any identity. Since mutants must be valid, mutation operators are syntactic patterns defined relative to particular programming languages. In the upcoming figure 1.1, it shows some mutation operators of the C language. Constraints are associated with mutation operators to guide selection of test cases likely to distinguish mutants from the original program. For example, the mutation operation SVR, which is nothing but the scalar variable replacement, can be applied only to variables of compatible type, that is only for the valid one, and a test case that distinguishes the mutant from the original program must execute the modified statement in a state in which the original variable and its substitute have different values. Here is a program of transduce which converts the line endings among the Unix and the DOS. Firstly, convert each line from standard input. Void transduce, we have to define the buffer length that is equal to 1000. Character buffer buff length. In this statement, it accumulates the line into this buffer. Next, int position is equal to 0. The index for the next character is the buffer over here. Character in char, the next character from the input. In at CR is equal to 0. CR meaning candidate recommendation. 0 is equal to within the line and 1 is equal to it's an optional DOS LF. While here in character is equal to get character, which is not equal to EOF. EOF meaning end of file. Switch of in character case LF if at CR, that is the optional DOS LF, at CR is equal to 0, else it is encountered CR within the line, that is emit buff is equal to position, position is equal to 0, and then we have to break down from that statement. Then the KCR emit buff comma position, position is equal to 0, at CR is equal to 1, and then again break, and the default statement is if the position is greater than or equal to buffer length minus 2, then it fails. Buffer overflow. Buffer, if the position is incremented, then in character. If the position is less than 0, emit buff comma position, and here the program ends. SSR, construct for scalar replacement. Replace scalar variable x with struct field s, that is x not equal to s. CAR, constant for array replacement. Replace array reference a of I with constant c, and its constraint is a of I is not equal to c. SAR, scalar for array replacement. Description is it replaces array reference a of I with scalar variable x, and its constraint is a of I not equal to x. Fault-based adequacy criteria. It consists of few steps. Here is a program and test your T mutation analysis, which consists of the following steps. Select mutation operator is the first step. If we are interested in specific classes of faults, we may select a set of mutation operators which is relevant to those faults. Second step, generate mutants. Mutants are generated mechanically by applying mutation operators to the original program. Third step, distinguish mutants. Execute the original program and each generated mutant with the test case in T. A mutant is killed when it can be distinguished from the original program. A mutant can remain live for two reasons. The first reason is that the mutant can be distinguished from the original program, but the test suite T does not contain a test case that distinguishes them. That is, the test suite is not adequate with respect to the mutant. Second reason for this is the mutant cannot be distinguished from the original program by any test case. That is, the mutant is equivalent to the original program. A set of mutants SM and a set test suite T, the fraction of non-equivalent mutants killed by T measures the adequacy of T with respect to SM. Unfortunately, the problem of identifying the equivalent mutants is undecidable in general, and we could either be claiming that a mutant is equivalent to the program under test when it is not, or by counting some equivalent mutants among the remaining live mutants. The adequacy of the test suite TS evaluated with respect to the 4 mutants of figure 1.2, which is in the further slide, is 25%. However, we can easily observe that mutant MI is equivalent to the original program. That is, no input would distinguish it. Conversely, mutants MK and MI seem to be non-equivalent to the original program. There should be at least one test case that distinguishes each of them from the original program. Thus, the adequacy of TS measured after elimination, the equivalent mutant MI is 33%. Mutant MI is killed by test case mixed, which represents the unusual case of an input file containing both DOS and Unix terminated line. DOS is nothing but disk operating system. We would accept that mixed would also kill MK, but this does not actually happen. Both MK and the original program produce the same result for mixed. This happens because both the mutant and the original program fail in the same way. The use of simple oracle for checking the correctness of the outputs. Example, checking each output against an unexpected output would reveal the fault. The test suite T is to obtained by adding test case mix to TS would be 100% adequate relative to this set of mutants after removing the fault. Here are few IDs with operators and the line number with original or mutant and with few test cases. The test cases include 1U, 1D, 2U, 2D, 2M, end, long and mixed. ID MI ROR line number 28. The position is greater than or equal to buffer length minus 2 and position is equal to buffer length minus 2. Here no mutant is killed. MJ operator ROR line number 32. Position is greater than 0. Position is greater than or equal to 0. In test case 1D, 2U, 2D and 2M, the mutant is killed. MK SDL line number 16. At CR is equal to 0. Nothing. Here no mutant is killed. MI SSR line number 16. At CR is equal to 0. Position is equal to 0. Mixed mutant is killed. Here are the test case description. 1U, one line Unix line end. 1D, which means one line DOS line end. 2U, two lines Unix line end. 2D, two lines DOS line end. 2M, two lines Mac line end. End, which describes last line not terminated with line end sequence. Long, very long line, which is greater than even the buffer length. Mixed, mix of DOS and Unix line ends in the same file. Here I complete with my topic. Thank you. Have a nice day.